All right, the first thing we're going to do is the new advanced version or level 2 right-hand rule game. I'm very nice in this game. I actually give you the answer. Answer C. Question is, what's the second vector? So F cross something gives you B. So F, really what I'm asking is, in which direction do you turn your fingers so that your thumb points in the direction of B? Now, according to the observation made by students earlier, all three axes must be used in this problem. B is a left-right. F is an in-out. So the missing one must be up-down, D or C. So if you go F in, the only way that you can get your thumb to point to the right is if you move your fingers up the page towards D. So the answer is F cross D is equal to B. So F, D, B. Now for the second one, I don't give you the first part. I give you the second and third. Blank cross A is equal to C. So A is left, right, C is top down, which means our choices are either E or F. So A, we can go either out of the page and we get D, or A, or I'm sorry, So we have to start with either E. E is out of the page towards the back of the room. A is that way, so the thumb points towards the floor, which is C. So let's do it incorrectly. I'll show you how incorrectly. If we start with into the page, or F, A is still this way, so the thumb would point towards D. That's not the answer that we want. We want C. So what you do is you flip your direction. You go E towards the back of the room. A towards that side, which gives you C. So E cross A down the page is C. Do you see that? Yes. Well, now that our expert in right-hand rule is here, Amy, could you tell me, and in fact, that would be kind of nice if the answer was M in the middle for number 3. But what is number 3?
Number 3, let's see, A is this way. So, would it be C?
It would be C. It is C. So A is the first vector. I have a choice. I can either go C or D to get the thumb out of the page. To get the thumb out of the page, my hand is naturally in this position already. A cross C, thumb points out, or E. Okay. Blank cross A is equal to F. So F is in or out, A is left, right. So I either have to start with D or C. So if I started with D and went A, that points out, or E. That's incorrect. So the answer must be C cross A, which is into the page or F. The last one, D cross blank, is B. So D, I got to get B for my thumb to point out. And so that, I either have either E or F. If I chose F, I'd be pointing in A. So it has to be E to point to B. So that's the right-hand rule. And so for those keeping score at home, it's those. And how I make this is I typically do the right-hand rule. I do the right-hand rule thing, and then I just take the letters out that I want to be missing. All right. What we're going to first do is one of the tests. We'll do oh wait, it's not that pile, it's this pile. What I'm going to do is, this will be test 2 from last summer term, July 20th, 2016. What we're going to do is we'll just go over the multiple choice and then we'll do the problems. And then we'll keep on moseying on. So what I do now is I just copy and paste all the equations that you would need for the whole semester into it. A lot of these can be repetitive from test 1. I'll probably take, like for this was a problem that we covered in test 1, so I doubt that it would be in. Same with this. Let me get this zoomed up. Which one of these 5 is at the center of a circle of current? C. Now 4 could be a legitimate problem. Circle dot is a vector that comes what? E out of page. Induced flux is opposite of the change in flux is what? C, Lenz's law. Magnetic flux, phi sub b, is what? It is C, B times A. Now, 2 parallel wires have currents that are parallel to each other. So the 2 currents look like this. What will the wires do? Will they attract each other? Will they repel each other? Well, let's think about this. The B field for this guy, oh, hold on, thank you. The B field, and actually what I'm going to do, the lower wire is the green one. It produces B field out of the page. Above the green wire, it produces B fields into the page below the wire. We know that the force on the wire direction is I cross B. So I on the upper wire is to the right, B is up. So it will feel a force that is downward. Here, the B field below this wire is into the page, and above the wire it is out of the page. But at the wire that we're studying, I cross B means that the force is pulling the bottom one up. So really what's happening is that it looks like they attract each other. And what will happen is that the wires will bow inward like that. If the currents were anti-parallel, the wires would repel each other. And you can kind of think of it like, this is a lot like a circle of current. If
the circle of current, basically the way that it does is it would repel each other. The natural way for a current to go through a wire, and if it's just hovering there, if you had kind of like mushed it up into an irregular shape, the forces on that wire would cause it to pull outward until it's a circle. Ideal voltmeter, probably get rid of that. Voltmeters are hooked up to blank into a circuit. It is attached to parallel to, probably take that out. You are holding a negative particle in the B field going from left to right. There is no gravity. You gently let go of the particle, so its initial velocity is 0. It does what? So if I gently let go of this particle and its initial velocity is 0, what's the force on the particle? Kind of a trick question. What's the force on any charge moving in a magnetic field? What equation? Oh wow, I hate students. Do the same thing. What? F equals Q times what? VB. Excellent. So if I let go of that charge and its velocity is 0, what's the magnetic field?
Would it go down?
Why would it go down?
Because it would have no force acting upon it.
Now I specifically said there was no gravity. So if there's no gravity, what's the magnetic force on the particle? If its initial velocity is 0, its magnetic force is therefore 0. So it wouldn't do anything. It would just, if there was no initial velocity, the particle would just sit there. If I threw the particle, it now has a velocity and it would bow however Q V cross V looks like. So a wire with current from ceiling to floor is in front of you. The B field vector from the wire at your position is what? Now, what you would do with this is you would use the wrap rule. Thumb goes down. On the left, it is into the page. On the right, it's out of the page. But really, if you were looking at it from the perspective of from the ceiling, this is you originally in this frame of reference. The B field would look like that. Into the page, away from you, out of the page, towards you, which means that the B field at your position is from right to left. You pass across a battery from the negative to the positive lead. Your change in V is what? Someone almost said it. It's positive, yes. You pass across a resistor against the current. Your change in V is what? What? You said E? E is in easy? Or E is in
Easy.
not excellent? Passing across the resistor, it has to deal with IR. If you're going against the current, it's positive IR. if you're dealing with the battery, you have to have the information of, am I going from which pole to which pole? For a resistor, the main criteria is, am I going against or with the current? Non-ideal ammeters, we've covered. A wire with current from left to right is stretched in front of you. The B field from the wire at your position is, so looking at this, it's coming at you at the top, away from you at the bottom, which really means that to go from there to there, the B field in front of you is top to bottom. So if we were looking at it from, let's see, try to draw this in 3D. So now what we're going to do is we're going to have the vantage point from the ceiling. So there's the wire going from left to right. You're here, you're in front of the wire. Above the wire, which we can't really show, so above the wire I'm going to use red. It comes at you. Beneath the wire, it comes below the wire. So it's really, what it's doing is it's coming up on the behind and down in front. So it's kind of looking like this. This is from the edge position. So this is above, this is from that perspective with relationship to the wire. So it comes down in front of you. Electromotive force being dependent upon the change in magnetic flux is what? It's E, Faraday's law. So when you're talking about electromotive force and change in flux, we're dealing with Faraday's law. If you're talking about the induced flux being opposite of the change in flux, that's Lenz's law. You are a negatively charged particle. You walk into a room, so you're negative and you're walking into a room. The B field is from left to right. So V is into the page, B is to the right. So V cross B is down, but you're a negative particle, so your magnetic force is up. You flip the sign. Why are you smiling? Did you just understand the problem?
No, I didn't.
All right. So the magnetic field is from left to right. So it's going from there to here. Now granted, I'm a professor, so I'm naturally negative. But my velocity, so I'm walking into the room. Which direction is my velocity vector? It's forward towards the board. So V, and actually, don't use your left hand. V cross B points to the floor, which means that I should feel a force that makes me go down like this. But I'm a negative particle, which means what I do is V cross B, and I'm a negative particle, so I flip. So what happens is that as I walk in, I bank up.
So it's negative V cross B. Do you get it now? Okay.
Can you show that right hand again?
All right. Right-hand rule for a charge in a moving magnetic field is Q, basically the sign of Q, times V cross B. V vector and B vector. B vector. So V is that way into the room. B is to the right, because I said so. That means V cross B points down. If I was a positive particle, the force would be down. But I'm a negative particle, so you have to flip. So negative V cross B points up. So I'm curving up towards the ceiling. Convert to my, oh, well, I don't like this one. That one. Now, for number 19, let's go over the basics of what baseball is. Home plate, first base, second base, third base, pitcher in the center. The pitcher throws a negatively charged ball from the mound to first base, which means that the velocity is in this direction. The B field goes from the sky to the ground. So the B field is into the ground. It's a negatively charged particle. So V is towards first base. B is into the page, which means that V cross B is pointed at second base. But it's a negative particle, which means you got to go V cross B, which means it points down, which means it curves towards home plate. Not at home plate directly, but it curves towards it. So
you say just always think about fingertips in the direction of velocity and based on the
remember what? So the right-hand rule for that particular case: V cross B. V is your first vector. B is your second vector. So V, and then you twist V wherever direction it goes, and then the resultant is V cross B. If it's positive, you just keep it as it is. If it's negative, you flip.
Is it also true for like when it's you have the negative sign on the front, you can do B cross B? Instead.
You could do B cross B, but then the negative sign would get absorbed, and then you would just do B cross B. I think that's overthinking, a little bit of overthinking it, but yeah, could be. Actually, you know what? Yes, negative of B cross B is equal to B cross B. But I like to think of it this way.
I always do confusing with this,
I just go V cross B. Is it positive? Okay, keep it. Is it negative? Flip. Is that too much?
so.
You just don't like the whole idea of moving your thumb?
Yeah, I don't like it.
Okay, fair enough. I don't judge. I just grade harsh. Uh, 20 may not, most likely won't be on it. Positive particle moves from left to right. It accelerates. The direction of the electric field must also be in the same direction. Yeah, I'm taking out the non-ideal stuff. Non-ideal voltmeter has a resistance of about 10 megohms. Take out ammeter. Magnetic field. I'm gonna get to 23 in just a second. 23. Wire with the current from right to left is stretched across the room. You turn on the external magnetic field, floor to ceiling.
the wire, so for this, it's I cross B. Oop, yeah. So I is in this direction. B is up the page. And actually, I'll do it in front of the class. So it's I cross B. I is this direction. B is in this direction. So the force on the wire is into the page. So the answer is, it will bow away from you. It will bend away. You are 1 meter away from a wire with current. You double your distance from it. The B field at the new point. So with a wire, B is mu naught I over 2 pi R. If you double R, you cut B in half, so it's 50% of its new position. And so that's the multiple choice. All right. Okay, problems. Well, okay. The appetizers, the right-hand rule, we're gonna do it like what we did at the beginning of class. Just so that I can do this. All right, F cross C is E. E cross F is C. E cross C is B. D cross B is A. A cross D is B. So what I would do is I would write this stuff down and then blank out one of these on each line and then see if you could do it again. But reason it from the blanks to begin with. All right, let's do some problems. So here, typically what I do, just to make things easier, is my circuits tend to be very simple. My J1 and J2, all clockwise. Think of them as current lines or current number lines for my current velocities. I'm gonna have 2 loops to put together. This is loop 1, this is loop 2. So I have to set up the loops. I go first across a 42 volt battery from negative to positive, so 0 equals positive V1. The next step, I go with J1 across R1. And the last step, I go with J1 across R3, but against J2. And that's the first loop. The second loop, I go with J2 across R3, but I go against J1 across R3. The second stage, I go with J2 across R2, and I go from negative to positive on V2, so I go positive V2. And so those are the 2 equations. Factor out the J's. So V1 minus J1, R1 plus R3 plus J2 R3. Plug in the values. V1, 42. R1 is 77 and R3 is 35. So it is, why did I choose those numbers? Those are crazy numbers. 102. And then J2 times R3 is 35 J2. Now for this, factor out the J's. In this case, it will be minus J2, R3 plus R2, J1 R3 plus V2. Plug in the numbers, minus J2. R3 plus R2 is 135. Oop, hold on, there. R3 is 35, J1 and V2 is 70. Now, I think why did I pick these numbers? These are weird. All right. I'm going to solve for J1 up here. So this is 102 J1 is equal to 42 plus 35 J2. So J1 is 42 plus 35 over 102. Kind of bizarre.
Should be minus 35.
You are correct. You corrected yourself. It shouldn't be negative. It should be positive.
7 plus 35 is 158.
Say that again.
7 plus 35 is 112, not 102.
Ooh, that fixes it. Yes, so 112. And thank you. Thank you for your incorrect answer. Thank you for your correct answer. So it's 112. And in fact, now, all right, that's why I was like, that's an odd thing because 112 is divisible by 7. So 42 divided by 7 is 6 plus 5J2 over 16. So that clears it up. In fact, in the test, each of these equations will be divisible by something so that you can clean it up. So in this case, because the thing that was bothering me, this is a test from last year. I know stuff can be divided because I wrote the thing, and I haven't written a Kirchhoff's law problem in a test that isn't divisible in like 4 years. So it had to have been divisible, and when I had 102, I'm like, that's just wrong, and she caught it. Plug this into here. Now this obviously is divisible by, did I get that right? Yeah, I did get that right. Oh, it's all divisible by 5, duh. So it's minus 27 J2 plus 7 J1 plus 14. So I'm reducing that down and simplifying it. Plugging J1 into there, I get that. Say it again.
Can you pull the page up?
Oh. Now, what am I going to do? Multiply everything by 16. Distribute. I'm going to pull my J2s over to the other side. So this is actually 432 J2 minus 35 J2 is equal to 42 plus 224. This gives me 397 J2. That gives me 266. So J2 is 266 divided by 397, and it's positive. Now, yeah, I was playing games with the numbers. From a decimal perspective, because that's a prime number. Well, it's not prime factor, I think. You can't reduce it anymore. But the thing about this number that's so interesting is it's 0.67003. So 0.67 amps is what I would accept. You see that double zero coming after that number. That's me trying to work the numbers so that it would work out. Now that I have J2, I can get J1. J1 is 6 plus 5, 0.67 over 16. And I get 0.58 amps positive. Yeah. So it's a positive, which means that the current for I1 runs like this. The current for I2 runs like that. Both of them are clockwise. They meet head on. So I have a 0.58 down and a 0.67 up. The 0.67 comes from I2. The 0.58 comes from I1. So we're going to get I in the middle to be the bigger one minus the smaller one. 0.09 amps. And since 0.67 is bigger than 0.58, the current goes from bottom to top. And so that's a Kirchhoff's law. Any questions on this? Yes?
How do you know if they're both going clockwise? How do you know that J1 was going down and J2 is going up?
Well, through the particular, let's say we just had two loops side by side. Both have a clockwise current. when you look through those boxes in this middle region, the left loop has current going down. The right loop has current going up at that middle region. And so that's why. Yeah, plus plus minus minus is a little bit weird because you're gonna have to figure out which one's the bigger one and then find the difference. In the plus minus or minus plus, that's easy. You just add up the magnitudes and you're done. Okay, number 2. We have a circular situation. A is static, B is not. I want to know if the current is running counterclockwise, will the B field reach positive 3 Tesla or negative 2 Tesla? And I want to know the time at which it achieves that goal. The current is going counterclockwise. In fact, I'm going to draw it bigger initially. So the induced current is counterclockwise. The induced current produces a induced B field and flux and all that stuff that is out of the page. Because we know that the external change in flux is always opposite of the induced change in flux, the change in magnetic flux with respect to time must be in. To get the change in magnetic flux with respect to time to be in, and B field is the only thing that changes, the dB dt must be in. So the dB dt is less than 0 or has a negative slope. So what happens is it's 0.5 for the B field. The slope is negative, which means it's not going to reach 3 Tesla. It will reach negative 2 Tesla or 2 Tesla into the page. Now let's get some equations set up. B final is equal to B naught plus dB dt times time. The electromotive force, in terms of its magnitude, is d phi b dt, which is also A dB dt. The current is electromotive force divided by R, which is equal to A over R dB dt. So I have my A, I have my R and I, so Ri over A is equal to dB dt. So already we know the answer is it will reach negative 2 Tesla first. The next question is when? Substitute that into this. So B equals B naught plus Ri over A T. Solve for time. B minus B naught Ri over A T, A over Ri, B minus B naught is equal to T. And we get that. So plug stuff in. 0.8, 4, 0.2, B is negative 2 minus B naught, which is 0.5. Why is this time gonna be negative?
The current's counterclockwise, so does that make it negative?
I don't think, hold on, B minus B naught. Oh. I know what I did wrong. R times I over A is just the magnitude of dB dt. And I know for a fact that the slope is negative because we reasoned it through that it has to be negative. So this value is not plus, it's minus. So that's where the signs flip, because you can't have negative time. And
Wait, will you explain why it's negative?
okay, hold on. All right, in order to get the negative sign there, we have to manually put it in. Why do we know this? The current is counterclockwise. That means that the induced flux must be out of the page. To get the induced flux out of the page, the external change in magnetic flux must be in. For the external magnetic flux to be in, and A does not change, that means the dB dt is into the page, which means that that value of dB dt must be negative. So if I just said, well, give me the value of the change in magnetic field, what I would do is I would take R, which is 4, times I 0.2 divided by the area 0.8, and that gives me the magnetic field, which is 1. That's the magnitude, and because that the B field change is into the page, the dB dt is equal to minus 1 Tesla per second.
What number did you just plug in right there?
That's R4, I is 0.2, area is 0.8. And then you get that.
Area given or?
Area is given, yes. And so that's problem 2.
What's the case whenever dB dt would be like out of the page?
Let's say if the current was clockwise. So if the current, let's say the current was clockwise. Hold on. If the current was clockwise, the induced magnetic flux would be not out, but in. Lenz's law says that the external must be out. To get the external to be out, the B field must be out as well. And so, yes,
Can you just go back to the first, like, big circle that you wrote everything in? Thanks.
so in the case where the current is counterclockwise, the external change in flux is into the page. And then we do if we're going to treat that as a magnitude, you do this. If the current is reversed, then you're going to have a plus sign. In this case, the B final would be -2. In this case, the final B would be, according to the rules, 3.
So the change in the magnetic field over time and the change in the magnetic flux over time will
Be
all
parallel.
be parallel.
For this problem, yes. For the circle problem,
But for the other one, it's not.
it's a different type of problem.
We will do that.
Yeah, we'll do one of those after problem 3. All right.
Mecklenburg?
Hmm?
So with the circle problem, is it safe to say then always, like, counterclockwise, you'll have a negative dV over dt, and then vice versa?
If it's counterclockwise, yes. Yeah. You could sit there and go through, like on, when we did 2 days ago, yesterday, because we went through all 4 permutations. You can see that. You can see that. All right, problem 3. Problem 3 has 3 wires. Oh my goodness. First wire goes from right to left, has an I1 of 0.1 amps. Wire 2 is to the right. I2 has a current of 0.2 amps. I3 has a current going from right to left, but I don't know what it is. In fact, I'm looking for that. I know for a fact that at a distance of 0.1 meters below, that particular point has the B field of 0. The distance there to there is L1, which is 0.2. The distance from there to there, L2, is 0.3. And in the problem, I call it X. So the first question is, what is the value of I3 such that the B field at that point is 0? So the total sum of the B's is equal to 0, which is B1, B2, and B3. We're going to have sums of these. For 1, it's the red line. Using the wrap rule, current or B field goes into the page above and below, it is out of the page. Wire 2 will do green, out of the page above, into the page below. And then green, because I got no, or blue, because I have no other color. For that, it is into the page above and out of the page below. So B3 and B1 will both be positive. B2 will be negative. 0 equals mu naught I1 over 2 pi R1 minus mu naught I2 over 2 pi R2 plus mu naught I3 over 2 pi R3. I could factor out the mu naught and 2 pi and just chuck them. So they all go away. If I multiply everything by 2 pi over mu naught, they disappear. Which means I'm left with I1 over R1 minus I2 over R2 plus I3 over R3. The question is, I need to find I3. So I2 over R2 minus I1 over R1 is equal to I3 over R3. And we have that. Multiply both sides by R3. And we get this. R3 is the distance from the wire to the point. That wire to the point is 0.1, or just x. I2, 0.2. R2 is the distance from there to there, 0.3 plus 0.1, or 0.4. I1 is 0.1. R1 is the distance from there to there, 0.2 plus 0.3 plus 0.1, or 0.6. So I3 gives me 0.033 repeating amps, or you could just say 33 milliamps. Now the question for the second part, which direction will wire 3 bow? What we need to do is we need to find the B field at wire 3 from the contributions of the first 2 wires. So really what we need to do is we need to find the magnetic field strength from the first 2 wires at that point. So we need to find B1 plus B2. And that equals to mu naught I1 over 2 pi, the new R1 for part 2. It's positive because anything below that wire is positive. Anything below this wire is negative. So it's minus mu naught I2 over 2 pi R2. This becomes mu naught over 2 pi I1 over R1 minus I2 over R2. 4 pi 10 negative 7 over 2 pi I1 0.1, R1 the distance from there to there, or 0.5, minus I2 0.2 divided by its distance, or 0.3. Now really what I'm looking for, I'm actually not interested in the total number. What I'm interested in is the sign of that portion right there. And I end up with a negative number. Just for completion, we're gonna figure it out. And I get negative 9.3 times 10 to the negative 8 Tesla. So the B field at this particular point is into the page. So here's my wire 3. The current is going from right to left. The total B field at those points are into the page. We know that the wire has a force on it of I cross B. So I, B, thumb points down, so the force, the magnetic force, is down the page. And so that's the answer for number 3. It's just simple addition, and then understanding that the direction is that. Okay. Since we have a request, we will do a moving bar problem. We have So one of the things that I would like to know is, and this will be the choice of the class, is the bar moving to the left or right? Moving to the left, okay. Let's say that do you want the B field in or out? In, okay. So the B field magnitude is 0.5 Tesla in. The length of the bar is 4 meters. The resistance is 4 ohms. The velocity is 16 meters per second to the left. The question is, what is I? What is the external force? And give me the direction of that external force applied to it such that the velocity remains constant. Now, in this particular case, the flux is into the page. So the initial flux is down here. The window is closing, which means that there is less flux getting through it. So if we were to plot the flux, it would look like that until it reached 0 when the area was 0. Which means that the d phi b dt is positive, or we would say out of the page. So the d phi b dt is out of the page. That means that the induced flux or induced magnetic field has to be into the page as well, or has to be into the page. Lenz's law demands that this is opposite to this. To get that, the induced current must be clockwise. Because if we look at just that one wire segment from left to right, or I'm sorry, current goes from right to left, the B field goes into the page on that side and out of the page on the other, so it has to be like this.
So how did you decide to slope that graph goes up like that?
I know that the magnetic flux is initially negative. It has a negative value. Why? The B field is into the page, has a specific area. But the area is getting smaller, which means that the magnitude of the magnetic flux is going to decrease. It's going to go from negative 0.5 or whatever to negative 0.4 to negative 0.3, which means that the slope of the flux is positive. Sort of like if you're walking backwards at 5 meters per second, and then it's 4 meters, negative 4 meters per second, negative 3 meters per second, the change in slope or the change in velocity will have a positive slope. Or the velocity plot will have a positive slope. Blech. So Lenz's law says this has to happen, which means that the current induced has to be clockwise. If you have a current going from top to bottom, I comes at me, B is into the page, which means that the magnetic force as it should be is opposite of the velocity of the bar, which, excuse me? Okay, hold on. The current from here is going from the ceiling to floor. The B field is going in. So V down to the ground, B into the page. The magnetic force is to the right. So if the magnetic force is to the right, the externally applied force to keep that velocity constant must be to the left. External force is always opposite of the magnetic force. And magnetic force is always opposite of V. You can also say that the external force is always parallel to V, or in the same direction. Now let's do some equations. That's all just the physical sciencey part, the English part. The electromotive force, now we're dealing only in magnitudes. We know all the signs, but in terms of magnitudes, this works. The EMF is d phi b dt. Magnetic flux is B times A. B doesn't change, A changes, so this is B dA dt. Current is that, so current is this. Now area is L times X. So dA dt is L dx dt. L doesn't change, but X does. This means that dA dt is equal to LV. So I is BLV over R. B is 0.5, L is 4, V is 16, R is 4. So the current is 8 amps. To get the magnetic force, we know that the magnetic force is ILB. The current is 8. The length is 4. The B field is 0.5 or 16 newtons. If the magnetic force is 16 newtons, then the external force applied is 16 newtons, but in the opposite direction. So we would say 16 newtons left.
How do you find the actual value for d5b over dt in the problem set?
What you can do, it depends on the situation. For d5b dt, really, the d5b dt is the electromotive force. So the answer that you give for d5b dt is in volts. In this case, EMF is B dA dt, which is BLV. We've shown that. This is the change in magnetic flux with respect to time. So B is 0.5, L is 4, V is 16. So it is 32 volts. And that's how you would find it. You would just find the BLV part of that. And so that's a typical bar one. I need to, hold on, let me remind myself. Because I have all of these done really nice, and we can look at them. Yes?
So you would call this the moving bar problem?
Yeah, I call it a moving bar problem.
So this wasn't one of the ones you said was gonna be on the test?
It's either this one or the circle.
Okay, gotcha,
The moving bar is changing area.
gotcha.
The circle is changing B.
Okay.
It's got to be one of those two. Which one? I don't know. I'll probably write it all on Monday, since the test is on Tuesday. So for problem, the thing, we're familiar with the multiple choice. We're familiar with right-hand rule. We're familiar with Kirchhoff's law. We're familiar with the moving bar or circle problem. The wild card is going to be the third problem. The third problem, just to say it out loud, B field addition. I would say the awesome ones would be problem 3 from test 2 of summer 16. I would say that problem set 6, number 5. Now for problem set 6, just work on it, get it done. The big ones that I want you to work on are problems 1, 2, 4, maybe, and 5. You can, if you want to take a shot at 3 and 6, have at it. They're not going to be on the test, and I'm not going to bother grading them. Hopefully I told the grader not to grade them. Problem 4, take a stab at it and get that done. For more the B field addition, problem set for numbers 7 and 8. That will give you a good shot at all of that. As for a moving particle in a B field, I would look at I would definitely look at problem set for number 4. And then look at the instructions, or this basically the stuff where I'm talking about mass spectrometry. The third one is force on a wire in a B field. And I would look at, so we got today, all weekend, and on Monday. Wow, we got a lot of time. Number 7, problem set for number 7. The only other one that would really, problem set 6, 2, and 4. I haven't really decided what I'm going to do with this. What probably is going to happen is, and you've seen it before, is I'm going to sit down for today and over the weekend, kind of munch on these problems and see what I'm going to do. I pretty much, the first 2 problems are boring, and the right-hand rule is boring, and the multiple choice is boring. I got to think about this. I'm not sure, so I'll kind of think about it, and then on Monday probably I'll be a little bit more firm on what I understand the third problem to be. It's got to be one of these 3. B field addition, magnetic force on a wire, moving particle in a B field. I'm kind of partial to I'm kind of feeling that particle motion, charged particle in a magnetic field for some reason. I don't know. Honestly, I don't know why I'm thinking that, but I feel that the problems that you're given for force on a wire in a B field are kind of weak. So if I'm gonna do, if Vegas is betting, I'd probably go 45, 45, and 10 percentage. So moving particle in a B field or B field addition would probably be what I'm leaning towards. Now, I don't know for sure. I haven't written it. But you want to know my thoughts, there it is. All right, if we could kill another 10 minutes or so, I'd be happy. Because I mean, we can't leave a full half hour before. Yes, we can? Yes, we can! Yeah. So, does anyone we'll do one kind of interesting problem and then we'll be done. Unless, hold on, if I've got the time. Do you want me to see, or do you want me to do the vector addition problem from test 1 in front of you? You're saying no. No, not right now? Okay. What do you want to see?
Why don't you do one of those that we haven't done?
One of these that I haven't done. Okay. Actually, I had one person just blatantly flat out say, do the one that's going to be on the test. And I don't know. Some of these are just so,
Whichever one's gonna take like 8 minutes.
what?
Whichever one takes like 8 minutes.
Okay. So right now I'm feeling this. You have a velocity selector pipe. And the particle is positive. The E field in this velocity selector is 50 newtons per coulomb, and the magnetic field is .2 Tesla. The charge on this guy is 5 times 10 to the negative 6 coulombs, and the mass is 1 times 10 to the negative 3 kilograms. So the first question that I have is, what's the velocity of this thing in order for it to pass through the velocity selector? Well, we know that it's a positive particle. The E field, I'll have this drawn out. The E field is from left to right. So what happens is that the electrical force is QE. The B field is into the page at 0.2 Tesla. So V cross B means that the magnetic force, because it's a positive particle, is to the left. That magnetic force is QVB. In order for the particle to pass, the forces must sum up to be 0. FB is to the left, FE is to the right. So FB is equal to FE. So QVB is equal to QE. So V is equal to E divided by B. E is 50, B is 0.2, so the velocity is 250 meters per second. Now what happens is this positive particle comes shooting out into a region where the B field continues to be 0.2 Tesla in. The B field is in, but there is no electric field. There is no electric field. The first question is, does the particle bank left or right? And I kind of did the problem already, or that question already. A charge on the force on a particle in a magnetic field is what? Q times V cross B. V is that way, B is into the page, force is left. which means this thing is going to bank like that. The major questions that I have now are, what is that distance d? And what's the time that it took for it to travel and impact from the time that it entered the magnetic field? Once it enters the magnetic field with no electric field, it is in rotational motion, circular motion. So the sum of the forces radially must equal to mv squared over r. There's only one force acting on this thing, and that's QVB, the magnetic force on a charged particle in a magnetic field. The V's cancel, and what I'm left with is mv over QBR. So that's the radius of this thing. And what we know is that the radius is d over 2. So this is mv QB d over 2, or d is 2mv over QB. So 2 times 1 times 10 to the negative 3, 250. Q is 5 times 10 to the negative 6. Oh, that made B is 0.2. We're going to get a diameter of, or a distance of, a long, long, long way. 500,000 meters. Wait, did I do that right? Hold on. Yeah, okay. 500,000 meters. On the test, this is a dynamically created problem, so that it's, I'll get the distance down to like 5. But the distance is now 500,000 meters, or 500 kilometers, so it's a particle spectrometer the size of a state, or states. Velocity is distance over time. Time is velocity, or I'm sorry, time is distance over velocity. So 500,000 divided by 250. 50,000 divided by gives me 2,000 seconds. So it would take roughly 40 minutes or so, 35, 40 minutes for it to go over an impact. And so it could be something as simple as this. Velocity selector and this. So in this, the last question, we've been good enough. The last question is, positive particles will bank left. What types of particles will bank right? Negative. What particles won't bank at all? Neutral. There we go. All right. I'll have office hours if you want to talk to me. Have fun in lab, then go home. That's it.